Hello, welcome to Deterministic Optimization. I'm Shabir Ahmed. I'm one of the co-instructors of this course. In this lecture, we're going to review some basic concepts from linear algebra. Let's get started. So our learning objectives are, as I just mentioned, we're going to recall some basic concepts from linear algebra. You should be familiar with a lot of these concepts, but we'll just review it for the sake of completeness. Okay, so a vector is an n tuple of real numbers. So it can be thought of a point in n-dimensional space. So the notation, if you remember, this is boldface x is a vector, r is a set of real numbers, and this is a vector of size n. So basically we have n numbers arranged as such over here, where each of those numbers are real numbers. And this can be thought of as a point in n-dimensional space where the first coordinate corresponds to the first number in the vector and so on. Typically, we'll consider column vectors throughout this course. So whenever I write down a vector, think of this as a column vector where the numbers are stacked on top of each other. Then the transpose of this column vector is going to be a row vector, that is where the numbers are arranged in a side-by-side fashion. So you should know the standard vector operations like sum of two vectors, assuming that these vectors are of the same dimension. These are of the same dimension, they're of the same size. The sum of two vectors is the component-wise sum of the coordinates. Similarly, the difference of two vectors is the coordinate-wise difference. And then multiplication of a vector by a scalar, where alpha here is a scalar, means that you multiply each coordinate by that scalar. The magnitude of a vector we're going to consider is going to be what is known as the L2 norm, or sometimes called the Euclidean norm. Let me write this down. So Euclidean norm. Okay. Essentially, this means that you square each coordinate, you sum it up, and you take the square root, right? So it's the usual notion of a size of a vector. Now, the scalar product, or sometimes called the inner product or the dot product between two vectors of the same dimension, is defined as, so here's what is x. This is the scalar product, x transpose y, where you multiply each coordinate of x and y together and you sum up across all of the coordinates. It is a scalar product because this product returns a number, right? So this would be a number. You sum up over each coordinate. Also, it is known that the scalar product is essentially, so this expression here, where the scalar product between two vectors of the same dimension is equals to the magnitude of the first vector times the magnitude of the second vector times cos of theta, where theta is the angle between the two vectors, right? So remember that what we just said, that a vector can be thought of as a point in space. Like for example, here in this picture, I have a two-dimensional space and there are two vectors. This point is the origin, and this is the coordinates of the vector. So that's the x vector. That is the coordinates of the y vector, and that is the y vector, so drawn. And so there is a clear understanding of what the angle between these two vectors are. This is theta, and so what this tells you that the dot product between these two vectors is essentially magnitude of x times magnitude of y times cos of theta. So here, for example, another way to think about it, if you think of the y vector, so this is the length of the y vector, and if you multiply that by cos of theta, you get this part, right? So that's magnitude of y, cos of theta, that's equal to the dot product divided by the magnitude of the x vector, right? So this is how much this is in proportion to the magnitude of the x vectors. Okay, so from this expression, we can see that the two vectors are orthogonal, which means that they make a 90-degree angle if their dot product is 0, right? They make an acute angle, which means an angle which is less than 90 degrees, if their dot product is positive, because cos of an angle which is less than 90 degrees is positive, and an obtuse angle if their dot product is negative, which means that the angle between the two vectors is obtuse. Okay. Now let's talk about linear independence. So a set of vectors, here I have x1, x2, xk, these are all vectors, k vectors, in n-dimensional space, so in Rn, are linearly independent if none of the vectors can be written as a linear combination of the other vectors. Okay? So I cannot take one vector and write it as some scalar sum of the other vectors. So another way to think about it is, so if I write down this equation, so where basically I take each vector, multiply it by a scalar and sum it up and set it equals to 0, and then these scalars, the unique solution to this system of equations. So notice that this is a system of equations, right? Because on the left-hand side, I have n equations. On the right-hand side, I have n numbers, right? So it's a system of equations. And the unique solution of this is that all of the scalars will have to be 0, right? If this system admits a solution where one or more of the scalars is not 0, then the vectors are not linearly independent. This is a useful fact and a very well-known fact that there are at most n linearly independent vectors in Rn, right? So we cannot have more than n linearly independent vectors. Now, any collection of n linearly independent vectors in Rn defines a basis or a coordinate system. So what is a basis? Essentially, a basis is a set of vectors using which we can represent any other vector in that space, but just writing down a linear combination. So again, just to repeat, any vector in Rn can be written as a linear combination of the basis vectors. So the usual basis of Rn are just what are called the unit vectors, right? So the vectors that define the coordinate system. So here, like E1 is a vector which has a 1 in the first position and 0 is everywhere else. That represents the first coordinate, right? So if I was to draw a two-dimensional thing, so this would be the first coordinate vector. E2 has a 1 in the second position and 0 is everywhere else. That's the second coordinate, and so on. Now, any vector in this space, in this two-dimensional space, can be represented as a linear combination of these two unit vectors, right? So clearly, essentially you just pick up the coordinates and multiply E1 by the corresponding coordinates and so on. And so that defines a basis. These are linearly independent. There are n of them, and they serve as a coordinate system, and this is known as the standard basis of Rn. Okay. Now, what is a matrix? A matrix is a rectangular array of m times n numbers with m rows and n columns, right? So here's a kind of a basic notation for a matrix. Here, so we have mn numbers, and each of them are arranged in this way. So alternatively, you can think of a matrix, it's a collection of n columns, right? So you have n column vectors, here's 1, here's 2, all the way to n of them. There's n column vectors, and the notation here is that I write a dot 1. This means that this is the first column of the matrix. Dot means that you're including all the rows. And so on. And so each of these columns are m-dimensional, right? So there are m numbers in each of these vectors. Or we could think of it as a collection of m row vectors, right? So here is a row vector, 1, here's a second row vector, and then there are m of them, right? So that's another way to think about a matrix is in this form. So I take all the vectors that define the rows of my matrix and just stack them on top of each other. And each of these row vectors are n-dimensional. Okay? Now let's recall the standard matrix operations, right? So remember that if I have two matrices of similar dimension, both involving m rows and n columns, we can define their sum or their difference. So that's why I wrote a plus and minus. So C is the sum or the difference, where it's essentially you just take each element of the matrix and you add them or difference them. That gives you the element of the new matrix. The usual notion of a matrix product, of course, they have to satisfy dimensions. So if A is an m by k matrix, you can multiply it by another matrix which has to have, if A has k columns, the other matrix has to have k rows, right? So I can take A, which is an m by k matrix, multiplied by B, which is a k by n matrix, post-multiplied by B, and get a matrix product which is A times B, which is this matrix C, and which is defined in the usual way. So basically the ijth element of this product matrix is the sum of the elements from the ith row times the jth column, right? So it is important to remember that matrix multiplication is not commutative. So this is not, A times B is not equals to B times A, okay? Now, if I have a square matrix, and so a square matrix means it has the same number of rows as the same number of columns, then its inverse, if it exists, it may not exist, is a matrix, which is kind of denoted by A inverse, which basically, this is a matrix which if I pre-multiply or post-multiply the original matrix with that, I will get the identity matrix. The identity matrix, remember, is a matrix which has zeros everywhere except the diagonals. Of course, and also you should remember the determinant of a matrix. So it's in some way the magnitude of a matrix. We're going to denote it by either determinant of A or this kind of absolute value sign. And so here I've just given you kind of formulas for determinants of 2 by 2 and 3 by 3 matrices. And you can extend these to kind of higher dimensional size matrices. Okay. So let's now talk about matrix vector multiplication. So if I have a matrix which is an m by n matrix and I have a vector which is an n-dimensional vector, one way to think about this vector is as if it is an n by 1 matrix. You can think of it as an n by 1 matrix. So when I multiply A times X, which is right over here, I'm going to get m by n times n by 1, and that's going to give you an m by 1 matrix, or in other words, it's an m-dimensional vector. That's what this is. This is what y is. So this is the matrix vector multiplication, which is basically a special case of the matrix multiplication. And so here there are two ways of thinking about this new vector y. You can think of it as a linear combinations of the columns of A, right? So one way of thinking this vector y is that you take the jth column of A and you multiply it by the jth coordinate of the x vector and you sum it up, right? So this is a linear combination of the columns of A. Another way of thinking about this is that the ith row of this vector y is the scalar product of the ith row of A and X as written down here, right? So this is the y vector, and the first entry of the y vector is the scalar product of the first row of the A matrix times the X vector. So both of these different ways of viewing matrix vector products are going to be useful. Okay. So let's talk about rank of a matrix. So I have an m by n matrix. The row rank of A is the maximum number of linearly independent rows. Remember that a matrix, you can think of it as a collection of row vectors. So, and these row vectors may or may not all be linearly independent, but what is the maximum number of linearly independent vectors in that set of vectors? That's called the row rank. Similarly, you can think of A as a set of column vectors, and so what is the maximum number of linearly independent column vectors in that set is what is called the column rank. This is a standard fact from linear algebra that the row rank of a matrix is equal to its column rank, and that is known as the rank of this matrix A. Now, of course, the rank of a matrix can be at most, because of this fact, can be at most the minimum of the number of rows and the minimum and the number of columns. So in other words, so this can be, of course, it cannot be bigger than the minimum of m or n. And it is called full rank if the rank is actually equal to the minimum of m and n. That's the full rank. That's called what is known as a full rank matrix. Okay. So let's talk about systems of equations now. So here we have a matrix which is an m by n matrix. B is an m vector, and suppose that A is full rank. All right. So now we can write down a system of equations, right? So a system of m equations is given by this expression over here. So A is the matrix of the coefficients of the equation, X is the vector of unknowns, and B is the right-hand side of the system of equations. Again, remember that this is m equations, and then there are n unknowns. And when I say that the matrix is full rank, it means that these equations are all they're different. They're not like just linear combinations of the other equations, so they all matter, okay? So now, obviously, if the number of equations is more than the number of unknowns. If I have more equations than unknowns, the system has no solution. Right? If I have the number of equations or linearly independent equations is exactly equal to the number of unknowns, then the system has a unique solution. And what is that solution? You basically, you multiply both sides of this equation by A inverse, right? Because now A is a square matrix, M is equal to N, and it is of full rank, so the inverse exists, and so this gives you X equals to A inverse B, right? So that's the unique solution that you get when you have a system of equations where the constraint matrix or the coefficient matrix is square and full rank. And now if the number of equations is less than the number of unknowns, then the system has an infinite number of solutions. Right? So, and we'll talk about that when we talk about linear optimization. Okay. So now let's summarize what we just reviewed. So we just went through some very basic concepts from linear algebra. There are a lot more topics in linear algebra in general. So we will introduce additional concepts regarding linear algebra on an as-needed basis. All right. See you in the next lecture.